Hey guys, Mrs. Traver here. Today we're going to look at what shapes have symmetry. Our learning target is that you'll be able to identify reflection, rotation, and translation symmetry and be able to tell what common shapes have those symmetries. You'll know you're successful when you can describe different types of symmetry with proper vocabulary. Today we're going to look first at who was absent for a quiz. If that's you and you did not take the quiz yesterday, you need to come see me via email or Zoom so we can figure that out. We're going to take some notes on types of symmetry and graphing lines as a review, and then you'll have a homework assignment for today. Let's jump in and first look at, let's see, what shapes have reflection symmetry. So I've got a bunch of shapes here, and what I want to think about is reflection symmetry. So reflection symmetry is when there's an axis of symmetry, and it can be folded, is the way I think of it, is if it could have folded and been on itself, then it has reflection symmetry. A common example of this is if you were going to look at a heart, you could draw this piece of the heart, and then it was reflected across the line. That wasn't a really good one, but a heart has reflection symmetry. For example, it can get folded. So if I look at where I could get folds here and get the same one, I'm noticing on the kite I could fold it here and here. No, wait, I couldn't fold it on that top one. This one would not cover that whole piece. So we have to be careful on things like that, on where you can fold it. You don't want to just start filling things in too quickly. So if you want, I would pause my screen here. This is what my students in class are doing, is they have this printed out, and try to draw all the reflection lines you can on here. So take a minute and try that, and then we'll come back in a moment and I'll have some answers on the screen. Alright, let's see how you did. I think I got all of them. The hexagon had several. It went through all the sides in the middle as well as all the corners. The kite had that one that we did. A rectangle had 2, scalene triangle none, trapezoid none, equilateral triangle had a few, square had through the sides and the corners. The 2 isosceles triangles here and here both had 1. A circle, I didn't draw any because there's actually infinitely many on a circle, because you could cut it any way you want and it's going to be symmetrical. So that's an interesting one. I'm not going to draw them all because literally I can't. They're infinite. Take a look at the rest and see how you did. Other than that, we're going to move forward. Alright, in our e-text, there is a spiral tool. I'd like you to check this out with me. I'll show it to you on screen and then you can mess with it yourself. But there's this spiral, and I want to know if we rotate it, when will it be symmetrical to itself? So if I rotate it and I see the same figure, that's when it has rotational symmetry. So this is a link on our slideshow, or you can go to your textbook, to that problem 1-100 on section 126. So here's the spiral, and it says move the slider through 360 degrees. How many times does a spiral rotate back onto itself, aka have rotational symmetry? So here's 0 degrees, it hasn't moved at all. If I start sliding it, it's going to turn, and I can see that I'm approaching a time when it's going to be on itself right here. So there's 120 degrees, it rotated onto itself. So it has rotational symmetry at 120 degrees. And there's another one at 240 degrees. And the last one at 360 degrees. So let's notice some things on that. I think I have to go back into percent. There we go. So it was at, what would we say, 120 degrees, 240 degrees, and at 360 degrees it had rotational symmetry because it turned, this piece went onto there, and then this piece went onto there, and onto there. So rotational symmetry is something different to think about. Alright, let's look at this decagon for a moment. What reflections carry the decagon onto itself? So I know I have reflectional symmetry. I could go through all of those edges, and that would give me the decagon as well. But what about if I did rotational symmetry on this? How far would I have to turn it in order for it to still look like a decagon? And we did this example in the last one too, right? So notice there were 3 rotational symmetry degrees, and there were 3 tails to this spiral. On this one, the decagon has 10 sides. So I'm going to bet that if we turn it 1/10 of the way around, then like the top little corner will be on the bottom, will be on the next corner, and so on and so forth. So if we turn it 1/10 of the way around, then that'll work. 1/10 of the way around. So every 1/10 turn is rotational symmetry. But what is 1/10 of a turn? Let's think about it. A whole turn is 360. And if we turn 10 times, that's 36 degrees. So every EVERY, there we go. Every 36 degrees, it's rotational symmetry. So there's one. And then we also know we have all of those reflectional symmetries. And that's pretty much all we got. Translation symmetry is kind of weird, but look at that next. Oh, whoops, rotations, we already talked about that. All right, different idea. Here is a graph, and I want to know if it has reflection, rotation, or translation symmetry. So I'm looking at the line of the graph. Ignore kind of the coordinate plane. It's there for us to give ourselves some place and position. If I tried to reflect this in any way, the only way that I could reflect it is if it was some line perpendicular to our line. So that would flip the front to the back and so on. So that would work. So reflectional symmetry would work. Rotational symmetry, it would have to rotate all the way around 180 degrees to completely turn, or 360 degrees, which turning 360 doesn't do anything. It turns you right back around to your normal position. So we've got rotational symmetry as well. Translational symmetry is something different. That is when you move it up, down, left, or right. Up, down, left, or right. So if this one, if I moved it up or down alone, it wouldn't be on itself. For left or right alone, it wouldn't be on itself. But say I moved it up one and over one. So like this point went to, how do I do it? Up one, over two, there we go. So this point went to this point. And this point went up one, over two. Up one, over two. It's actually just using the slope. So this one has translational symmetry as well, and it's reflected on the slope. Let's look at the next one. Different idea. Let's see, reflection. I could reflect here, and it would map onto itself. If I rotate it in any way, the only way it'd go back to itself if I go 360 degrees. And translation symmetry, there's no way I could do that. Here's another one. All right, let's see, reflection symmetry. How would I reflect this? I don't think I could. If I try to draw a line anywhere, it's not going to map onto itself. It's going to flip. Rotational symmetry, only the 360, which that'll work for all of them. Translation symmetry, let's see. If I try to move this point, if I move it 2 to the right, then this point will become this point. If I move this point 2 to the right, it goes to here. That doesn't work. Maybe if I go 4, okay, so if I took this point and I moved it 4 to the right, 1, 2, 3, 4, that works. If I take this point and I go 4 to the right, 1, 2, 3, 4, that works. So translational symmetry, if we go 4 to the right, it maps onto itself. All right, I'm going to skip this one and let's move forward. Let's look at reviewing graphing lines. So this is something that comes up in your assignment today, and I want to review a couple problems with you. Our first step on these is to graph our y-intercept. And then our second step is to use slope to rise over run to the next points. So if you remember y equals mx plus b, that's the formula we're using. So first is our b, that's at positive 2. And I want to go through the y-axis because that's a y-intercept. Next I'll use slope, which is 1 over 4. So that's 1 over 4. I'm going to go up 4 and right. I'm sorry, up 1 and right 4. Up 1, right 4. And there's my line. I could also go down 1 and left 4 to find another point. That's it. Hopefully that jogged your memory a lot. Let's do one more. All right, so our b is 5. Let's put a point here at positive 5. And then our slope, m, is 2, or 2 over 1. So I'm going to go rise 2, run 1. Rise 2, I'm off the graph. What if we go down to left 1 instead? Down to left 1, that also makes a rise 2, run 1. I can do as many as I like that fit on the graph to make my line nice and pretty as best I can. And that's it. All right, let's look at our assignment today. I'm going to skip this slide for us and, whoops. Let's look at our assignment today. Let me go back to the beginning. Sorry about that. Here it is. 1, 2, 6, 10, 105 through 109. My screen's being crazy. Try those ones out, see how it goes. You'll see some symmetry problems. You'll see some graphing lines problems. If you have any questions, come see me on Zoom. Other than that, I will see you tomorrow. Bye.